Tonight, we're going to break down a question that sounds simple until you actually try to answer it. What happens if something crosses the one boundary the universe has never once allowed to be crossed? Most people think of the speed of light as a wall, a hard stop, the end of the conversation. But that's not what the mathematics says. The equations don't go silent past that line. They keep talking. They describe a strange, inverted territory where the ordinary rules of cause and effect start to bend, where mass behaves in ways that have no everyday equivalent, and where the universe seems to defend itself with more than just a speed limit. By the end of tonight, you'll understand why this barrier exists in the first place. What the equations actually predict lies beyond it. Why faster than light travel keeps almost working in the mathematics before physics quietly shuts the door. And what all of this reveals about how alone every civilization in the universe might really be. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something you already feel, even if you've never thought about it directly. Every photon that has ever existed, from the light leaving a candle to the light leaving a quasar billions of years ago, moves at exactly the same speed. Not approximately the same. Exactly 299,792,458 meters per second in a vacuum, a number physicists simply call c. It doesn't matter what emitted it. It doesn't matter how fast the source was moving when it let that photon go. The number never changes. Sit with that for a second, because it violates something your brain has trusted since childhood. If you're standing on a train, moving at 60 miles an hour, and you throw a ball forward at 10 miles an hour, an observer standing on the platform sees that ball moving at 70 miles an hour. Velocities add. That's not a law you were taught in school so much as a fact your nervous system absorbed the first time you rode in a moving vehicle and tossed something out the window. It is how the world appears to work at human scales, and for centuries nobody had any reason to doubt it applied everywhere. Then, in the final years of the 19th century, two American physicists named Albert Michelson and Edward Morley built an instrument sensitive enough to test that assumption against light itself. The prevailing theory held that light travelled through a medium called the luminiferous ether, a substance thought to fill all of space, and that the Earth's motion through this ether should cause light to travel at slightly different speeds depending on which direction you measured it. Michelson and Morley split a beam of light, sent the two halves along perpendicular paths, bounced them off mirrors, and recombined them, expecting to see a shift caused by the Earth's motion through the ether. They found nothing. No shift, no difference. The light moved at the same speed in every direction, regardless of the Earth's motion around the Sun. It was one of the most famous null results in the history of experimental physics, and for nearly 2 decades. Nobody had a satisfying explanation for it. The explanation came from a 26-year-old patent examiner working in Bern, Switzerland, who had been quietly obsessed with a single question since he was a teenager. Albert Einstein had spent years turning over an impossible scenario in his mind. What would happen if you could somehow run alongside a beam of light, matching its speed exactly? From your perspective, would the light appear frozen, an electromagnetic wave standing perfectly still in space? The trouble was that Maxwell's equations, the framework that had unified electricity and magnetism decades earlier, simply didn't allow for a stationary electromagnetic wave. A frozen wave isn't a wave at all. It isn't a solution the mathematics permits. Something had to give, And in 1905, Einstein decided it wasn't the equations of electromagnetism that were wrong. It was our assumptions about space and time. His resolution, published in a paper titled On the Electrodynamics of Moving Bodies, was radical in the truest sense of the word. He proposed that the speed of light is not just fast, it is fixed, absolutely and unconditionally, for every observer, regardless of their own motion. And if that's true, something else has to bend to make the numbers work out. That something is space and time themselves, not the speed of light. Space and time became the flexible quantities, and the speed of light became the one fixed point around which everything else had to adjust. This single postulate, when you follow its logic carefully, forces a cascade of consequences that most people never fully absorb even after hearing about them for years. If two observers moving relative to each other both measure the same beam of light travelling at exactly the same speed, then their measurements of distance and time cannot agree. They can't both be using the same ruler and the same clock and get the same answer for the speed of that light unless the ruler and the clock themselves are different for each of them. Space contracts. Time dilates. And perhaps strangest of all, simultaneity breaks down entirely. Two events that happen at the same moment, according to one observer, may happen at different moments, or even in a different order, according to another observer moving relative to the first. Neither observer is wrong. There is no referee, no master clock somewhere in the universe that gets to declare which observer has the real, true version of now. Every inertial reference frame is equally valid, and now turns out to be a much more local, much more personal concept than we ever suspected. This is why physicists describe special relativity as one of the most conceptually disturbing results ever confirmed by experiment. It isn't disturbing because it's hard to calculate. The mathematics, once you accept the postulates, is fairly straightforward algebra. It's disturbing because it dismantles something we treat as bedrock. The idea of a single shared present moment stretching across the universe, uniting everyone and everything at this instant, right now. Special relativity says that instant doesn't exist in any universal sense. It says the present is something each observer carries with them, shaped by their own velocity, and that two people moving differently through space are, in a very real sense, living in slightly different slices of time. None of this stayed confined to theory. Every consequence of Einstein's postulate has been tested, measured, and confirmed with a level of precision that borders on the absurd. Particle accelerators watch unstable particles survive far longer than they should because time is running slow for them relative to the lab. Atomic clocks flown on airplanes tick at measurably different rates than identical clocks left on the ground. The GP's satellite constellation orbiting Earth right now has to apply constant relativistic corrections just to keep your phone's blue dot accurate to within a few meters, because without accounting for time dilation, positioning errors would accumulate by several miles every single day. Special relativity isn't a hypothesis anymore, it's infrastructure. It's running quietly in the background of your daily life, whether you've ever thought about it or not. But here's the piece that matters most for where we're headed tonight. Buried inside this same framework, inside the very equations that describe how time slows and distances contract as you approach light speed, is a mathematical description of what happens if you keep pushing past it. Einstein's equations don't simply refuse to answer the question of faster than light motion. They answer it in full. And the answer is one of the strangest results in all of theoretical physics. To understand why, we first need to look at exactly what happens to an object as it approaches the light barrier. Because the resistance you meet on the way there is the same resistance that defines what waits mathematically on the other side. Picture a spacecraft with an engine capable of unlimited thrust, burning fuel indefinitely, accelerating at a steady 1g, the same pull you feel standing on Earth's surface right now. For the first year, everything proceeds the way your intuition expects. The ship gets faster. The crew feels normal gravity. Nothing seems strange. But something invisible is already happening beneath the surface of that ordinary experience, something that becomes impossible to ignore as the ship's velocity climbs into a significant fraction of the speed of light. The quantity that governs this is called the Lorentz factor, usually written as the Greek letter gamma. The formula looks intimidating at first glance. 1 divided by the square root of 1 minus velocity squared over the speed of light squared. But the behavior it describes is simple to follow even without doing the arithmetic yourself. At rest, gamma equals exactly 1. Nothing unusual happens. As velocity increases, gamma creeps upward, almost imperceptibly at first. At 10% of light speed, gamma is barely different from 1 about 1.05. You would never notice the effect without instruments sensitive enough to detect nanoseconds of difference. But the curve isn't linear. It doesn't rise gently and predictably the way most things in daily life do. It rises slowly, then faster, then explosively, curving toward an asymptote that never quite arrives. At 50% of light speed, gamma is about 1.55. At 90%, it jumps to roughly 2.3, meaning time for the traveller is now passing at less than half the rate experienced by someone who stayed behind. At 99%, gamma reaches about 7. At 99.9%, it's around 22. At 99.99%, it exceeds 70. Each additional decimal point of speed demands a dramatically larger investment of energy than the one before it, and the returns in terms of how much closer you actually get to the speed of light itself keep shrinking. This is not a limitation of engineering. This is not a problem that better engines or more efficient fuel could someday solve. It is a structural feature of space-time geometry as fundamental as the fact that a circle can't have corners. The reason lies in the relationship between energy, momentum, and mass, formalized in an equation more complete than the famous E equals mc squared most people remember from a classroom wall. The full relationship states that the square of an object's total energy equals the square of its momentum times the speed of light squared, plus the square of its rest mass times the speed of light to the 4th power. For anything with non-zero rest mass, that mass term never disappears, no matter how much energy you pour into the system. As velocity climbs towards c, the energy required to produce each additional increment of speed grows without bound. To reach exactly the speed of light would require infinite energy. Not an enormous amount, not more energy than currently exists on Earth. An amount that has no upper boundary, a quantity so large the very word amount starts to lose its meaning. Only one category of object escapes this constraint entirely, and it does so not through some clever trick, but because it lacks the very property that creates the constraint in the first place. Photons have zero rest mass. Look again at that full energy equation, and you'll see that when rest mass is 0, the entire mass term vanishes. Leaving a much simpler relationship, energy equals momentum multiplied by the speed of light. A massless particle satisfies this equation only by moving at exactly c, always, under every possible condition, with no other velocity available to it. It isn't that photons happen to move fast, it's that massless existence and motion at exactly the speed of light are the same statement, phrased two different ways. There is no such thing as a slow photon or a stationary photon. Because a photon at rest is not merely rare, it is mathematically non-existent. This creates a boundary unlike any other boundary in physics, a line that doesn't separate two continuous ranges of the same kind of thing, but separates two entirely different categories of existence. On one side sits everything with mass, forever approaching C and forever forbidden from touching it. On the other side sits light itself, permanently locked at C, with no ability to slow down even if it wanted to. And it's precisely because this line is so absolute, so categorically different from an ordinary speed limit, that physicists began asking, decades ago, what the equations say if you imagine something existing purely on the far side of it, not accelerating through the barrier from below, which the mathematics forbids outright, but starting out already beyond it, the way a photon starts out already at it. This is where the story stops being about propulsion and starts being about geometry, about the strange internal logic of Einstein's equations when you feed them a variable they weren't designed for. Because the Lorentz transformations, the mathematical machinery underlying all of special relativity, do not simply return an error message or a blank page when you substitute a velocity greater than c. They return an answer, a complete, internally consistent, mathematically valid answer, describing a regime that behaves like a photographic negative of the physics we live inside. Where ordinary particles struggle harder and harder to gain speed as their energy increases, this other regime describes something that gains speed as its energy decreases, approaching C from above the way ordinary matter approaches it from below, but never quite touching it from either direction, as though C itself were a mirror with two entirely different worlds reflected on either side of the glass, one of matter and one of something else entirely. And it's worth pausing here on what this actually means, because there is a tendency, especially among people encountering this idea for the first time, to imagine physicists simply plug a bigger number into the equation, get a valid result, and declare victory. That isn't what happened. What happened is stranger. The equations describing this other regime produce a value for mass that isn't a normal number at all. It's what mathematicians call an imaginary number, a quantity involving the square root of -1. In most contexts, encountering an imaginary result in a physics calculation is a signal that you've made an error somewhere, that the mathematics is telling you the scenario you've described cannot physically occur. And in a sense, that's exactly what it's telling you here too. But the specific way it tells you this, the specific mathematical shape of that impossibility, turns out to be extraordinarily informative. It doesn't just say no. It describes in precise and reproducible detail exactly what no looks like from the inside, what the universe would have to become for the answer to flip to yes. And that description, worked out rigorously by physicists starting in the 1960s, is where our story goes next, into a mirror world where energy and speed relate to each other backward, where cause and effect can trade places depending on who's watching, and where the very substance of what we call matter takes on a form with no true physical counterpart anywhere we've ever looked. In 1967, a physicist at Columbia University named Gerald Feinberg decided to take this mirror mathematics seriously and work out exactly what it would mean if such a particle existed. He published his findings in the journal Physical Review, and he gave these hypothetical particles a name drawn from the Greek word for swift, tachyons. Feinberg's approach wasn't reckless speculation. He was careful to point out that special relativity, strictly speaking, never says an object cannot travel faster than light. What it says is that no object can be accelerated through the barrier from below. That leaves open, at least on paper, a third category entirely separate from ordinary matter and from light itself, a class of particles that simply always move faster than c. The same way ordinary particles always move slower than c, and photons always move at exactly c. 3 regimes, 3 categories, each permanently sealed off from the others by the impossibility of crossing between them. What Feinberg discovered when he worked out the properties such particles would need to have was genuinely strange, and it wasn't strange in a vague, hand-wavy sense. It was strange in a precise, calculable way. For ordinary particles, adding energy increases speed, approaching the light barrier from below but never reaching it. For a tachyon, the relationship runs in reverse. Adding energy decreases its speed, pulling it down towards c from above, again without ever touching it. A tachyon with enormous energy would be moving only slightly faster than light. A tachyon with almost no energy at all would be moving at nearly infinite speed. Removing energy from a tachyon doesn't slow it down, it speeds it up further. It is, in the most literal mathematical sense, physics turned inside out. This inversion carries a consequence that goes well beyond strangeness into something closer to a genuine crisis for the logical structure of the universe. And it concerns the order in which cause and effect occur. Because special relativity tells us that different observers, moving at different velocities relative to each other, do not always agree on the timing of distant events. For anything travelling at or below the speed of light, this disagreement never threatens causality, because every observer, no matter how they're moving, still agrees on the basic sequence: cause first, effect second. The Lorentz transformations guarantee this. It's built into the structure of the mathematics. But for anything moving faster than light, that guarantee breaks down entirely. Under the right conditions, a signal that one observer sees travelling from point A to point B will be seen by a different observer, moving in a particular direction relative to the first as travelling from B to A instead. The source becomes the receiver becomes the source. And because special relativity insists that no reference frame is more correct than any other, there is no way to say which version of events is the real one. Both are equally valid descriptions of the same physical situation. In 1970, 3 physicists named Gregory Benford, David Book, and William Newcomb worked out exactly how bad this problem becomes if you try to build a device around it. They called their thought experiment the tachyonic anti-telephone, and it remains one of the cleanest demonstrations of why faster-than-light signaling cannot be permitted in a universe that behaves consistently. Imagine you build a transmitter capable of sending messages faster than light, and you aim it at a receiving station moving away from you at high velocity. Because of the relativity of simultaneity, that station, in its own reference frame, receives your message before you sent it. Confused but functional, it immediately transmits a reply using its own faster-than-light equipment. That reply travels back to you, and because of the same relativistic effect working in the opposite direction, it arrives in your hands before you ever sent the original message. You read the reply. You realize what's about to happen. You decide, reasonably, not to send the message that supposedly triggered it, which means the station never receives anything, which means it never sends a reply, which means nothing prevents you from sending the original message after all, which means the reply arrives again. It's a loop with no stable resolution, not a puzzle to be solved cleverly, but a genuine logical contradiction, a scenario in which an event both happens and does not happen, depending on which point in the loop you examine it from. Benford, Book, and Newcomb weren't describing science fiction. They were demonstrating, with rigorous mathematics, that faster-than-light communication and a logically consistent universe cannot coexist. Something has to give, and every scrap of evidence we have says it isn't the consistency of the universe that gives way. Given how thoroughly this idea was worked out on paper, it's worth asking the obvious question: has anyone ever found a tachyon? The honest answer, after more than half a century of dedicated searching, is no. Particle accelerators at facilities including CERN and Fermilab have hunted for signatures consistent with Feinberg's predictions. Detectors have been built specifically sensitive to particles with the properties tachyons would need. The result, across every experiment ever conducted, is a complete and total null result. If tachyons exist anywhere in nature, they interact with ordinary matter so weakly or exist in such vanishingly small numbers that no instrument humanity has ever built has caught so much as a hint of one. Combined with the causality problems demonstrated by the anti-telephone thought experiment, most physicists today regard the tachyon in its original 1960s sense of an actual faster-than-light particle zipping through space as a mathematical curiosity rather than a genuine feature of our universe. An answer the equations were willing to give, but one that reality, so far, has declined to provide. And yet the word tachyon didn't disappear from physics after this. It simply changed meaning, migrating from particle physics into an entirely different branch of theoretical work, where it describes something real, something measured, something that shaped the very structure of the matter you're made of. To understand that shift, you have to stop thinking about tachyons as objects racing through space and start thinking about them as a description of instability itself, a warning sign built into the mathematics of quantum fields, telling you that a system is sitting somewhere it cannot remain. In quantum field theory, every type of particle in existence is understood as a ripple, an excitation, in a field that stretches across the entirety of space. There is an electron field, and what we call an electron is a localized disturbance in that field. There is an electromagnetic field, and a photon is a ripple moving through it. The mass of each type of particle is tied to the shape of the potential energy landscape belonging to its field, and that shape can be pictured, without losing much accuracy, as something like a bowl. A particle corresponds to a small oscillation near the bottom of that bowl. The steeper the walls of the bowl, the more energy it takes to displace the particle and the higher its effective mass. A perfectly flat bottom describes a massless particle. But not every field sits comfortably at the bottom of a bowl. Some fields, under certain conditions, find themselves balanced instead on top of a hill at what physicists call an unstable maximum. In that configuration, the mathematics that describes the field's mass comes out negative when squared, which is precisely the condition Feinberg had identified decades earlier as the signature of a tachyon. Except here, nothing is racing through space faster than light. Here, the tachyonic condition describes a field that cannot remain where it is, a system perched at the top of a hill, destined to roll downward toward a genuine, stable valley the instant anything nudges it. The word hasn't lost its original meaning entirely. It still describes something forbidden, something the universe won't tolerate as a permanent state. It has simply shifted from labeling a fugitive particle to labeling a doomed configuration, a field waiting to fall. The single most consequential example of this kind of instability in the history of the universe involves the Higgs field. The same field responsible for the fact that you and everything you're made of has mass at all. In the earliest moments after the Big Bang, when the universe was still almost unimaginably hot, the Higgs field sat at exactly this kind of unstable maximum. Its true ground state, the configuration of lowest possible energy, existed elsewhere on its potential energy curve. But the field hadn't reached it yet. In that primordial, symmetric state, electromagnetism and the weak nuclear force weren't yet separate forces. They were unified into a single interaction, and every fundamental particle that would eventually acquire mass through interaction with the Higgs field was, for a brief cosmic instant, entirely massless. As the universe expanded and cooled below a critical threshold, the Higgs field could no longer remain balanced at that unstable peak. It rolled downward, settling into its true minimum in a process physicists call the electroweak phase transition. And the consequences of that single rolling motion, that transition out of a tachyonic state and into a stable one, rewrote the entire architecture of physical reality. Electromagnetism and the weak force split apart into the distinct interactions we observe today. The W and Z bosons, which carry the weak force, gained substantial mass through their coupling to the newly settled Higgs field. Electrons, quarks, and every fundamental fermion that makes up ordinary matter gained mass as well. Before that moment, there was no chemistry because there were no atoms with a defined size, no electrons bound in stable orbits, nothing capable of forming the bonds that chemistry depends on. After that moment, the raw material for stars, planets, and eventually you existed for the first time. The particle physicists eventually detected at the Large Hadron Collider in 2012, after a search stretching back nearly half a century, is the Higgs boson, a ripple in the field around the stable valley it now occupies. It is, in a sense, the fossil record of that ancient instability, direct evidence that the Higgs field once sat somewhere it couldn't stay, and that its fall from that unstable peak is the reason mass, and therefore structure, and therefore you, exist at all. The tachyon, in this sense, did real work in the early universe. It didn't fly anywhere. It didn't carry a message backward in time. It described an impossible balancing act that the universe was never going to maintain, and its resolution built the physical world we inhabit. A similar story unfolded in an entirely different corner of theoretical physics. In the earliest versions of string theory developed in the late 1960s and early 1970s. The simplest version of the theory, known as bosonic string theory, produced a lowest energy state for its fundamental strings that was tachyonic, an unstable ground state signaling that the theory as originally formulated wasn't describing a genuine stable universe. Physicists recognized this immediately as a serious problem, not a minor technical wrinkle. A theory whose vacuum state is unstable isn't really describing a vacuum at all. It's describing a system perpetually on the verge of collapse into something else, something the theory itself couldn't specify. The resolution came through the introduction of supersymmetry, a deeper symmetry pairing particles of different quantum character, which restructured the theory's mathematics in a way that eliminated the tachyonic ground state entirely. The resulting superstring theories settle into genuine stable valleys rather than unstable peaks. And this resolution is part of why superstring theories are taken so seriously as candidate frameworks for unifying gravity with quantum mechanics, even though whether any of them correctly describes our actual universe remains a completely open question. What emerges from both of these stories, the Higgs field and early string theory, is a consistent pattern in how tachyons actually function within physics. They are not fugitives from the light barrier, hypothetical racers slipping past a speed limit. They are diagnostic tools, warning signs embedded in the mathematics that flag when a theory, or a physical field, is sitting somewhere it cannot remain. They mark instability. They point toward the direction a system must fall to find genuine stability. And in every confirmed instance where physics has actually put this concept to use, the tachyon's role has been to describe a transition toward a more settled state of reality, never to describe an object outracing light through the vacuum of space. So if faster-than-light particles remain, at best, an unconfirmed mathematical possibility with serious causality problems attached, and at worst a concept that's been fully repurposed to mean something else entirely, does that close the book on this question? Not quite. Because there's an entirely separate route into the same territory, one that doesn't involve particles moving through space-time at all, but instead involves the shape of space-time itself. And this is where the conversation shifts from the physics of Einstein's special relativity to the far stranger, far more geometric territory of his general theory of gravity, a theory that, it turns out, may leave a door open that special relativity slams shut. General relativity, published by Einstein in 1915, reframes gravity entirely. It isn't a force reaching out across empty space the way Newton imagined it. It's the geometry of space-time itself, curved and warped by the presence of mass and energy, with everything else, planets, light, falling apples, simply following the straightest available path through that curved landscape. What we experience as being pulled toward the ground is, in this picture, nothing more than following the most natural trajectory through space-time that has been bent by the Earth's mass beneath our feet. The geometry tells matter how to move, and matter, in turn, tells the geometry how to bend. This relationship is captured in Einstein's field equations, a set of 10 interlocking, non-linear equations connecting the distribution of mass and energy to the resulting curvature of spacetime. These equations, unlike simpler physics formulas, don't have one tidy solution. They have many, each corresponding to a different possible configuration of mass, energy, and geometry. The Schwarzschild solution describes the spacetime around a non-rotating black hole. The Kerr solution describes a rotating one. Other solutions describe the large-scale expansion of the universe itself, and buried among these many valid mathematical solutions are a handful that describe something else entirely. Structures that look, on paper, like genuine shortcuts through the fabric of spacetime, connections between distant points that don't require crossing the intervening distance at all. The first hint of this came remarkably early, in 1935, when Einstein and a colleague named Nathan Rosen were studying the mathematics of the Schwarzschild black hole solution using a different coordinate system than usual. What they found was startling. The interior geometry of the black hole examined this way didn't simply terminate at a singularity. It connected, mathematically, to a second, separate region of space-time, distinct from the exterior the black hole had originally formed from. This connection became known as the Einstein-Rosen bridge, and in diagrams it resembles nothing so much as a tunnel linking two otherwise disconnected regions of the universe, regions that might be separated by enormous distances, or might not even belong to the same universe at all. For decades this remained a mathematical footnote, and for good reason. Careful analysis showed the bridge was fundamentally unstable. Its geometry evolved dynamically over time, and the throat connecting the two sides pinched, closed far too quickly for anything, even a beam of light, to complete the crossing. Worse, anything approaching from the black hole's exterior would have to cross the event horizon first, placing it on an unavoidable path toward the crushing tidal forces of the singularity long before it ever reached the bridge itself. The Einstein-Rosen bridge was real mathematics, describing a genuine feature of the Schwarzschild geometry, but it offered nothing resembling a usable route from one place to another. It sat quietly in the literature, a curiosity rather than a possibility, for more than half a century. Then, in 1988, everything changed, and the origin of that change is almost charmingly ordinary. Carl Sagan was writing a science fiction novel, and needed his protagonist to cross interstellar distances without violating known physics. So he asked physicist Kip Thorne, then at Caltech, whether general relativity permitted any such mechanism. Rather than dismissing the question, Thorne took it seriously, and working with Michael Morris and Ulvi Yurtsever, he published a paper in the journal Physical Review Letters titled Wormholes in Spacetime and Their Use for Interstellar Travel. The paper worked out, rigorously, what conditions a wormhole would need to satisfy in order to be genuinely traversable. No singularity blocking the throat, tidal forces gentle enough for a human being to survive, and a throat that remained open long enough for something to actually pass through it before it collapsed. What they found was that such configurations are mathematically consistent solutions to Einstein's equations. A spacecraft could, in principle, enter one mouth of a wormhole, travel through a relatively short throat, and emerge from a second mouth positioned potentially light years away, with the entire crossing taking minutes rather than millennia. Crucially, nothing inside the wormhole would violate the local speed limit. Light within the throat still moves at exactly c through its local geometry, but because the throat itself represents a genuine shortcut through the larger structure of spacetime, an outside observer would see the spacecraft complete a journey in far less time than light traveling the conventional route through ordinary space would require. It's not that anything inside the wormhole broke the rules, it's that the geometry itself found a way to cheat the distance. Every serious proposal of this kind, whether Thorne's traversable wormhole or the warp drive concepts that would follow it, runs immediately into the same requirement, a requirement that shows up again and again like a recurring theme in a piece of music. Holding the throat of a wormhole open against its natural tendency to collapse demands material with negative energy density, a substance physicists call exotic matter, meaning a region of space containing less energy than an empty vacuum would ordinarily have. This isn't as outlandish as it sounds at first. The Casimir effect, produced between two closely spaced conducting plates through restrictions on quantum vacuum fluctuations, genuinely does create a small region of reduced energy density below the vacuum baseline. And it has been measured in laboratories. The effect is real, but the amount of negative energy the Casimir effect produces is astonishingly small, and rigorous theorems developed by physicists Lawrence Ford and Thomas Roman, known as the quantum energy inequalities, establish strict mathematical bounds on how much negative energy any quantum field can produce within a given region for a given duration. The larger and longer lasting the region, the tighter those bounds become. For a wormhole throat large enough and stable enough to be genuinely useful, the amount of negative energy required vastly exceeds anything the quantum energy inequalities permit any real field to generate. The Casimir effect is a candle. A traversable wormhole would need something closer to the output of a star, and there is no known mechanism, not even in principle, capable of bridging that gap. It's tempting, hearing this, to file wormholes away alongside tachyons, an elegant mathematical possibility with no genuine path to reality. But there's a second geometric proposal, developed independently and refined repeatedly over the following decades. That takes a different approach to the same underlying problem, one that doesn't rely on tunneling through space-time at all, but on manipulating the space around a ship directly. And the story of how that proposal evolved from a wildly impossible energy requirement down to something almost within theoretical reach is one of the more remarkable arcs in modern theoretical physics. In 1994, a young Mexican physicist named Miguel Alcubierre was doing postdoctoral work at the University of Wales in Cardiff when he published a short paper in the journal Classical and Quantum Gravity titled The Warp Drive hyper-fast travel within general relativity. It's a modest 8-page paper, but it opened a line of inquiry that remains active more than 30 years later. Because Alcubierre had found something genuinely new, he wasn't the first person to wonder whether faster-than-light travel might somehow be reconciled with Einstein's equations, but he was the first to construct a mathematically precise space-time geometry describing exactly how it might work. One that respects the local speed limit everywhere, while still achieving an effective faster-than-light result on a larger scale. The insight at the center of his proposal is a distinction that sounds subtle but turns out to carry enormous weight, the difference between something moving through space and something being carried by space. Einstein's light barrier constrains objects moving through space-time. It says absolutely nothing about the motion of space-time itself, and we already have direct observational proof that space-time can, in fact, move faster than light on a cosmic scale. The universe is expanding, and galaxies sufficiently distant from us are receding at speeds that exceed c, not because they are physically hurtling through space at impossible velocities, but because the space between us and them is itself stretching. Each small interval of distance grows a little, and when you add up enough of those small increments across billions of light years, the total recession velocity climbs past the speed of light without a single local rule ever being broken. No signal travels faster than light in any local patch of that expanding space. The galaxy is simply being carried away by the fabric itself, and general relativity places no upper limit on how quickly that fabric is allowed to stretch. Alcubierre's question was whether this same freedom could be harnessed deliberately on a small controlled scale around a spacecraft. Could you engineer a bubble of space-time that contracted ahead of a ship and expanded behind it, carrying the ship forward at any chosen speed while the ship itself remained motionless, sitting in perfectly flat, ordinary space-time the entire time? The answer, worked out in the mathematics, is yes. He constructed a metric, a precise geometric description for exactly such a configuration. Inside the bubble, flat space-time, no forces, no acceleration, nothing unusual for the crew at all. Outside the bubble, far from its influence, also flat, ordinary space-time, undisturbed, and at the boundary between the two, a warping shell, where the geometry itself does all the work, contracting space in front of the ship and expanding it behind, effectively carrying the entire bubble across the universe at any speed at all, without the ship inside ever locally exceeding the speed of light relative to its own immediate surroundings. The physics community's response was not dismissal, because Alcubierre hadn't made an error. He had found a genuine, mathematically valid loophole in the structure of general relativity, a real solution to Einstein's field equations. But the loophole came, predictably by now, with the same recurring price tag. The warping shell at the boundary of the bubble, the region where space-time transitions from contracting at the front to expanding at the back, needed to be filled with exotic matter, material with negative energy density, and the earliest calculations of how much such matter would be required were staggering. Some estimates placed the requirement at a quantity of negative energy comparable to the mass energy of an entire planet the size of Jupiter, expressed as a negative quantity. Other early calculations were worse still. The mathematics was sound. The engineering was not merely difficult. It called for a substance that, as far as anyone could tell, simply doesn't exist in producible form anywhere. For a while, the warp drive metric sat alongside the Einstein-Rosen bridge in the same category, a genuine curiosity of general relativity with no plausible bridge, so to speak, to actual engineering. What kept the idea alive wasn't stubbornness. It was a series of genuine theoretical refinements that steadily chipped away at that impossible energy requirement. In 1999, physicist Chris van den Broek, working at the Free University of Brussels, discovered a modification exploiting a peculiar freedom available in curved geometry that has no counterpart in flat space. The exterior surface area of a region and its interior volume don't have to match. You can construct a bubble with a very small exterior surface while maintaining a spacious, comfortable interior for a crew purely through the mathematics of curvature. By shrinking the exterior of the bubble down to a microscopically small scale while preserving a livable interior, Van den Broek showed that the total exotic matter requirement could drop by many orders of magnitude, still hopelessly beyond anything achievable, but a fundamentally different scale of impossible than what Alcubierre had originally calculated. The refinements continued into the 2010s, when physicist Harold White, working at NASA's Johnson Space Center, revisited the geometry once more, replacing Alcubierre's original spherical bubble shape with a toroidal, ring-like configuration, and distributing the required exotic matter around that ring rather than across a full sphere. White's calculations suggested this adjustment could reduce the exotic matter requirement to something in the neighborhood of a few hundred kilograms, a quantity that remarkably would fit inside an ordinary room. Still entirely unachievable, because no known process produces negative energy density in any bulk usable form, but the nature of the problem had shifted in a genuinely meaningful way. It had gone from requiring more negative mass energy than exists in the observable universe to requiring a modest quantity of a substance we simply have no idea how to manufacture. The ceiling hadn't been reached, but it had been lowered dramatically and repeatedly by careful, rigorous, peer-reviewed work. The most systematic advance came in 2021 when physicists Alexei Bobrik and Gianni Martire published a comprehensive framework analyzing warp drive geometries not as a series of individual isolated proposals, but as a general class of solutions that could be studied all at once. They showed that every warp drive design, regardless of its specific shape or configuration, decomposes into the same three basic regions: a flat exterior, a flat interior where passengers would travel undisturbed, and a warping shell connecting the two, with all the meaningful differences between designs boiling down to exactly what fills that shell and how its geometry curves. By mapping this entire design space systematically, Bobrik and Martire uncovered something previous, more piecemeal research had missed entirely. Warp bubbles that move slower than the speed of light, so-called subluminal configurations, can in principle satisfy the standard energy conditions using only ordinary matter, positive energy density, nothing exotic required at all. A subluminal warp bubble of this kind could never outrun light to a distant star. It doesn't cross the light barrier and never will. But it could, in principle, carry passengers at a substantial fraction of the speed of light with absolutely no internal forces acting on them whatsoever, no crushing acceleration, no physiological strain, nothing beyond what the crew would feel sitting still. And the physics required to eventually build such a system, while still far beyond anything achievable with current technology, doesn't call for a substance that might not even exist. It calls only for very large quantities of matter we already understand, arranged with extraordinary precision. Bobrik and Martire also released a companion computational tool called Warp Factory, allowing researchers to numerically evaluate any proposed warp drive design, calculate its required matter distribution, check whether it satisfies known energy conditions, and test its stability, transforming warp drive research from a scattered collection of individual analytical papers into something resembling a genuine, organized field of study with real infrastructure behind it. None of this means a warp drive is coming anytime soon, or perhaps ever. But it means the field has matured over roughly 3 decades from a single 8-page curiosity into serious, systematic, peer-reviewed science, and that maturation itself tells you something important about how physics treats even its most exotic-sounding proposals, not by dismissing them outright, but by working them over relentlessly until either a genuine possibility or a genuine impossibility emerges with total clarity. And even setting the exotic matter problem entirely aside, even imagining someone somehow solved it tomorrow, a superluminal warp bubble runs headlong into an entirely separate category of obstacles. Obstacles that have nothing to do with material science and everything to do with the deep structure of causality itself. Imagine, for a moment, that the exotic matter problem simply vanished tomorrow. Suppose an engineer somewhere found a way to manufacture negative energy density in bulk, cheaply, safely, in whatever quantity a warp bubble might require. Would that be the end of the story? It would not, because a superluminal warp bubble carries with it a set of consequences rooted not in material science, but in the deep structural logic of general relativity itself. Consequences that would remain even if the exotic matter problem were somehow solved completely. The most severe of these is what physicists call the event horizon problem. When a warp bubble moves faster than light, something strange happens at its leading edge. No signal originating from inside the bubble, no matter how it's generated, can travel fast enough to catch up with that advancing front wall, because the front wall is, by definition, moving faster than anything inside the bubble could ever hope to communicate. This creates a genuine event horizon at the leading face of the bubble, a causal boundary functionally identical in its mathematical structure to the event horizon surrounding a black hole. And the consequences for anyone actually riding inside such a bubble are severe in a very literal, very practical sense. A pilot cannot steer it. Any command sent forward toward the leading edge to adjust course, to avoid an obstacle, to slow down, chases that boundary forever and never arrives. The bubble follows whatever trajectory it was given at the moment of departure, rigidly, permanently, with absolutely no capacity to respond to anything encountered along the way. It cannot even be stopped from the inside, because halting the bubble requires modifying the exotic matter distribution in its shell, and that modification requires a signal to reach the shell from within, a signal that once again simply cannot outrun the horizon it would need to cross. The crew, in the most literal sense imaginable, becomes a passenger with zero control over their own vehicle, locked into a predetermined path until either the ship reaches its programmed destination or something external, previously positioned at that destination, intervenes to collapse the bubble from outside. Layered on top of this navigational nightmare is a second problem, rooted this time in quantum mechanics rather than pure geometry. Event horizons, wherever they occur, emit thermal radiation through a process first worked out by Stephen Hawking in 1974. Near any horizon, pairs of virtual particles and antiparticles spontaneously form out of the quantum vacuum, as they constantly do everywhere in space. Ordinarily, these pairs recombine and annihilate almost instantly, leaving no lasting trace. But near a horizon, the pair can be separated before that recombination happens, with one particle falling across the boundary and the other escaping outward, and from the outside, this separation looks exactly like thermal radiation being emitted by the horizon itself. For the enormous, gently curved horizons of astrophysical black holes, this radiation is so faint it's essentially undetectable. But the tightly curved, rapidly moving horizon at the front of a superluminal warp bubble is a different story entirely, and unlike the radiation from an ordinary black hole, which spreads outward in every direction, the specific geometry of a moving warp bubble appears to focus this Hawking radiation inward, directly toward the interior of the bubble, directly at whoever happens to be riding inside it. The precise intensity of this effect remains an active subject of calculation, dependent on the specific details of bubble geometry, but the underlying mechanism itself is entirely standard physics. Horizons radiate. This is not a hypothesis. It's confirmed theoretical physics extended into a new geometric context. And it is built directly into the quantum structure that a superluminal bubble inevitably creates, which is precisely why subluminal warp bubbles, the kind that never actually cross the light barrier, don't generate this problem at all. They never form a leading-edge horizon in the first place, because they never move fast enough to outrun their own internal signals. And then there's a third obstacle, one that has nothing to do with either geometry or quantum theory directly, but with the simple, unglamorous fact that interstellar space isn't actually empty. It contains, on average, roughly one hydrogen atom per cubic centimeter, along with scattered dust grains, stray electrons, ions, and cosmic rays. A medium so thin that conventional spacecraft pass through it without the slightest concern. But for a superluminal warp bubble, this dilute medium becomes something far more dangerous. As the bubble advances, particles encountering its leading edge don't simply pass through unaffected. They become trapped in the compressed geometry of the front wall, accelerated to enormous energies by the interaction and unable to escape forward. Over the course of a journey spanning several light years, the bubble sweeps through a genuinely vast number of these particles, each one accumulating energy in that compressed leading wall throughout the entire voyage. When the bubble finally reaches its destination and its exotic geometry collapses, all of that accumulated energy releases at once in a concentrated, forward-directed beam of high-energy particles aimed squarely at whatever lies at the destination. The occupants inside the bubble throughout this entire process remain completely unharmed, shielded by the very geometry that caused the problem in the first place. But anything waiting at the far end of the journey would not be so fortunate. A superluminal warp ship arriving at a distant star system wouldn't simply arrive quietly. It would arrive trailing a potentially catastrophic burst of directed radiation, not as some rare malfunction, but as an inevitable, unavoidable consequence of the standard physics governing how a warp bubble interacts with the ordinary interstellar medium it has been sweeping through the entire time. Taken together, the exotic matter requirement, the navigational lockout created by the event horizon, the inward-focused Hawking radiation, and the catastrophic particle beam released at arrival form something that looks almost deliberate. A layered set of independent obstacles, each rooted in an entirely different branch of physics, all converging to block the same destination. It's tempting to describe this as the universe defending itself, though that phrasing is more poetic than literal. What's actually happening is simpler and, in its own way, more remarkable. The deep structure of physical law, worked out across general relativity, quantum field theory, and particle physics independently, keeps arriving at the same conclusion from completely different directions. And quantum field theory adds one final layer to this picture, a formal mathematical prohibition that doesn't depend on wormholes or warp bubbles at all, one built directly into the foundations of how particles and fields are allowed to interact with each other across any distance whatsoever. In quantum field theory, physical measurements are represented mathematically by objects called operators, and there's a requirement known as microcausality, that governs how operators describing measurements at separated points in spacetime must relate to one another, specifically for any 2 points separated in a way that no light signal could travel between them in the available time. What physicists call a space-like separation, the operators describing measurements at those 2 points must commute. In plain terms, this means measuring one cannot influence the outcome of measuring the other. No information passes between them. This isn't an assumption bolted onto quantum field theory from the outside for the sake of tidiness. It's a mathematical condition the theory must satisfy in order to remain consistent with special relativity at all, and every quantum field theory used in modern physics, quantum electrodynamics, quantum chromodynamics, the electroweak theory, together forming what's known as the standard model of particle physics, satisfies this condition without exception. The standard model isn't a rough approximation that happens to work most of the time. Its predictions match experimental measurements to a level of precision that borders on the miraculous. Quantum electrodynamics, the theory governing electrons and photons, predicts the electron's magnetic moment to an accuracy better than 1 part in a trillion, making it the single most precisely confirmed prediction in the entire history of science. If microcausality were violated anywhere within this framework, that agreement would collapse. It doesn't collapse. Microcausality holds, which means causal locality, the principle that influences cannot outrun light, isn't a separate add-on rule imposed on quantum mechanics. It's woven directly into the deepest, most thoroughly tested theory of nature that physics currently possesses. This is where quantum entanglement deserves careful, precise attention, because it's the phenomenon most frequently misunderstood as a loophole in everything just described. Entanglement is entirely real. When 2 particles become entangled, measuring the state of one instantly determines the corresponding state of the other, regardless of how far apart they are, and this has been confirmed experimentally across distances ranging from a few centimeters in a laboratory to thousands of miles using satellites to distribute entangled photon pairs across continents. On the surface, this sounds exactly like faster than light communication. It is not, and understanding precisely why reveals something important about the difference between correlation and information. When you measure your half of an entangled pair, the result you get is genuinely random. Quantum mechanics governs the probabilities involved, but it does not let you choose or predict which specific outcome you'll receive before you measure it. Your partner, measuring the other particle anywhere else in the universe, also gets a result that is, from their perspective alone, entirely random, indistinguishable from noise. The correlation between your 2 results, the fact that they're related in a specific statistical way predicted by quantum mechanics, only becomes visible when the 2 of you bring your separate measurements together and compare notes. And comparing notes requires ordinary communication, a phone call, a radio signal, a message physically transmitted at or below the speed of light. There is no way to encode a chosen message into your partner's results before they measure anything, because you have no control over what result they receive. The correlation is real. The information required to make sense of that correlation travels conventionally, and conventionally means no faster than light. This result carries a formal name, the no communication theorem, first proven rigorously by physicist Philippe Eberhard in 1978 and strengthened and extended by numerous researchers since. It establishes, with the certainty of a mathematical proof rather than a mere experimental observation, that quantum entanglement, in every form it takes, cannot transmit usable information faster than light. No experimental exception has ever been found. No theoretical loophole has survived serious scrutiny. Entanglement is strange, genuinely and deeply strange. Bell's theorem, confirmed through decades of increasingly rigorous experiments by researchers including John Clauser, Alain Aspect, and Anton Zeilinger, work that earned the 2022 Nobel Prize in Physics, proves conclusively that the correlations entanglement produces cannot be explained by any theory relying on hidden local variables. Something genuinely non-local is present in how quantum mechanics operates. But that non-local something remains permanently unusable for sending an actual message. The universe, it seems, arranged things so that quantum mechanics can be globally non-local in a statistical sense while remaining locally causal in every practical sense that matters for sending information from one place to another. It's strange. It is not and cannot be turned into an exploit. General relativity contributes its own formal version of this same prohibition, expressed through a set of mathematical statements known as the energy condition theorems. The weak energy condition requires that the energy density measured by any observer in any reference frame must be non-negative. The null energy condition extends a similar requirement to observers moving at the speed of light. Building on these, a set of results known as topological censorship theorems, proven in the 1990s by physicists John Friedman, Kristin Schleich, and Donald Witt, establish something remarkable in any spacetime that satisfies the averaged null energy condition. No shortcut through spacetime can actually be traversed. More precisely, any path that appears to enter and exit a wormhole can be mathematically deformed, continuously reshaped, into a path that never enters the wormhole at all, meaning the apparent shortcut is, in a rigorous topological sense, trivial, an illusion of geometry rather than a genuine bridge. Traversable wormholes require violating this averaged energy condition. Superluminal warp bubbles require the exact same violation. This is the precise, formal sense in which exotic matter isn't merely difficult to obtain. It's required by the underlying topology of the geometry itself, and the quantum energy inequalities discussed earlier narrow the amount of violation any real quantum field can actually produce down to levels far below what any genuinely useful shortcut would need. Between the topological censorship theorems on one side and the quantum energy inequalities on the other, the geometry of spacetime appears fundamentally and rigorously sealed against superluminal shortcuts, at least within the framework physicists currently trust, known as semi-classical gravity, quantum field theory layered on top of a classical curved spacetime background. Whether a complete theory of quantum gravity might eventually change this conclusion remains genuinely unknown. And it's worth being honest about exactly where that uncertainty lives, because it doesn't live in some vague, hand-wavy space of pure speculation. It lives at a specific, identifiable scale, the smallest scale physics currently recognizes. A scale so far beyond anything we can experimentally probe that even naming it feels almost abstract. And yet, it may be exactly where the final answer to tonight's question is actually hiding. General relativity and quantum mechanics stand as the two most successful theories in the history of physics, each confirmed to extraordinary precision within its own domain, and each fundamentally incompatible with the other in its current form. General relativity treats spacetime as a smooth, continuous geometric fabric, endlessly divisible, with no smallest unit of distance or time. Quantum mechanics, by contrast, is built entirely on discreteness, probability amplitudes, and quantized energy levels that jump in defined steps rather than flowing continuously. When physicists attempt to apply quantum mechanical rules directly to the gravitational field itself, the calculations produce nonsensical infinities, breakdowns that appear specifically at extremely short distances near what's known as the Planck length, roughly 1.6 times 10 to the negative 35th power meters. To put that scale in perspective, a proton, already far too small to visualize directly, measures roughly 10 to the negative 15th power meters across. The Planck length sits some 20 orders of magnitude smaller still, a gap so vast it's genuinely difficult to hold in the mind using any everyday comparison at all. This is the scale at which the smooth geometry of general relativity is expected to break down entirely, and where quantum effects on the very structure of spacetime itself are believed to become significant, no longer negligible background noise, but the dominant feature of reality. Every serious candidate theory of quantum gravity currently under development predicts that spacetime possesses some kind of underlying structure at this scale, structure that simply isn't present in the smooth continuum general relativity describes. Loop quantum gravity, for instance, describes spacetime as woven from discrete loops and interconnected networks, where area and volume themselves take on quantized minimum values, unable to shrink below a certain threshold no matter how you slice them. The smooth, continuous spacetime of classical general relativity emerges from this picture only as an approximation, valid at scales vastly larger than the Planck length, in much the way a smooth beach seen from a distance dissolves, on closer inspection, into countless individual grains of sand. String theory, approaching the same problem from an entirely different direction, describes spacetime as populated by tiny vibrating strings with an intrinsic length comparable to the Planck scale, at which point the very concept of space and time as a smooth classical manifold simply stops making sense. A third approach, called causal dynamical triangulations, builds spacetime up from discrete geometric building blocks directly, and studies which large-scale structures naturally emerge from that foundation. Across all of these otherwise quite different frameworks, one striking feature recurs: the causal structure of spacetime, the fundamental ordering of events into past, present, and future, along with the light cone separating what can influence what, emerges from the underlying discrete quantum geometry rather than being imposed on it as an external rule from outside. In this picture, the speed of light isn't a limit that some governing authority attached to spacetime after the fact. It's the natural maximum propagation speed inherent to whatever quantum structure actually constitutes spacetime at its most fundamental level. In much the same way the speed of sound through a particular material is fixed entirely by that material's internal properties. You cannot make sound travel faster through steel by pushing harder on it. The atomic structure of the steel itself sets an absolute ceiling on how fast a vibration can propagate through it, and pushing harder doesn't raise that ceiling. It simply generates more heat, more distortion, more resistance, everything except the one outcome you were hoping for. If spacetime is, at its deepest level, something like a discrete quantum network, then the speed of light represents that network's maximum propagation speed for any influence whatsoever, and exceeding it wouldn't merely be extremely difficult or extraordinarily costly in energy. It would be structurally undefined, in the same category as asking what temperature lies below absolute zero. Absolute zero marks the point at which all thermal motion ceases entirely, and you cannot go below it, not because of some enforced restriction, but because there's simply nothing left to remove once you've reached it. It's the flaw of the very concept of temperature. The speed of light may occupy exactly the same kind of position, not a limit on a continuous range of speeds that quietly continues on above it, but the actual boundary of what the concept of speed even means within this particular universe. The precise point at which the underlying geometry changes character so completely that moving faster stops being a coherent question at all. This picture fits neatly, almost suspiciously neatly, with everything we currently observe. It explains why the speed of light shows up consistently across the equations of electromagnetism, gravity, and quantum mechanics, three areas of physics developed largely independently of one another over the course of more than a century. It explains why the causal structure of spacetime remains identical for every observer, regardless of their own motion. It explains why every single measurement of Lorentz invariance, the underlying symmetry of special relativity, comes back confirmed without exception again and again across an enormous range of experimental techniques. But it's important to be precise about the limits of this confirmation too. None of it has been directly tested at the Planck scale itself, because the Planck scale sits so far beyond the reach of any conceivable experiment using known technology that the gap is almost impossible to convey honestly. The Large Hadron Collider, humanity's most powerful particle accelerator, reaches energies of a few trillion electron volts. The Planck energy sits at roughly 22 times 10 to the 19th power gigaelectron volts, some 16 orders of magnitude higher, a factor of 10 million billion beyond what our best instrument can currently achieve. We are not merely far from probing this regime directly. We may never get there, not with any technology remotely resembling what we have today, and possibly not with any technology at all. The discrete structure of spacetime, if it genuinely exists in the form these various theories predict, is therefore inferred through theoretical consistency rather than confirmed through direct experimental measurement, and that distinction matters enormously. It means the deepest possible version of tonight's question, whether the speed of light represents a truly unbreakable structural property of quantum spacetime itself, remains genuinely open, not resolved by any observation currently within reach, but also not arbitrary or baseless speculation either. The theoretical case behind it is unusually strong, built from multiple independent frameworks converging on the same conclusion despite starting from very different assumptions. The case against it remains, for now, largely speculative, and in physics, a strong theoretical case that still lacks direct experimental confirmation is precisely where the genuine frontier of human knowledge currently sits, the exact edge where the next real discovery, whichever direction it points, is most likely waiting to be found. What emerges from all of this isn't a single, tidy answer. It's a layered structure of conclusions, each one grounded in a different framework of physics, all of them converging, independently and repeatedly, on the same underlying result. At the first layer, special relativity, nothing carrying mass can reach the speed of light through any conventional propulsion mechanism, no matter how advanced. The mathematics here is airtight, and more than a century of increasingly precise experiments has found no exception whatsoever. This layer is, as close as physics gets to anything, settled. At the second layer, the formal mathematics of the Lorentz transformations describes a mirror regime above the light barrier, populated by particles with imaginary mass, where the relationship between energy and speed runs entirely backward from what we experience. This regime is mathematically coherent and, so far as more than half a century of dedicated experimental searching can determine, physically empty. No tachyon, in Feinberg's original sense, has ever been detected, and the causality arguments built around it make its existence deeply problematic even on paper. In modern physics, the word has been almost entirely repurposed to describe field instability, a concept that turns out to be enormously important, responsible for the very existence of mass in the universe, and one that has nothing whatsoever to do with faster than light particles racing through space. At the third layer sits causality itself, arguably the deepest and most consequential layer of all. Faster-than-light information transfer proves fundamentally inconsistent with the logical structure of the universe we inhabit. The tachyonic anti-telephone thought experiment makes this explicit and unavoidable. The no-communication theorem confirms it from within quantum mechanics. Microcausality enforces it mathematically within quantum field theory. The energy condition theorems constrain the geometric loopholes that general relativity might otherwise seem to offer. Across every framework physics currently possesses, and across every experiment ever devised to test it, the universe consistently, relentlessly prevents effects from preceding their causes. At the fourth layer, the geometry of space-time itself. A genuine mathematical loophole exists, expressed through wormholes and warp drives. And that loophole is entirely real within the mathematics of general relativity. But it is blocked, thoroughly and from multiple independent directions, by the requirement for exotic matter with negative energy density, by the quantum energy inequalities that sharply restrict how much negative energy any real field can actually produce, by the navigational lockout created by the event horizon problem, by the danger of Hawking radiation focused inward toward any crew, and by the catastrophic particle beam released at a superluminal ship's arrival. The subluminal versions of these same geometries, notably, remain potentially buildable using only ordinary matter, representing genuine, meaningful, theoretical progress. And they sidestep the causality violations that plague their superluminal cousins entirely. At the fifth and deepest layer, quantum gravity. The causal structure of spacetime may ultimately be a fundamental property of some discrete quantum geometry operating at the Planck scale. If that turns out to be correct, then the speed of light isn't a limit imposed on spacetime from outside at all. It's a property of spacetime itself, as intrinsic to it as the speed of sound is to steel. This final layer remains theoretically well motivated and, for the foreseeable future, entirely inaccessible to direct experiment. These 5 layers aren't 5 separate attempts to answer the same question from slightly different angles. They're 5 genuinely independent lines of reasoning, built on different mathematical foundations, tested through entirely different kinds of experiments, and they all arrive, without coordination, at the same conclusion. And there's a piece of this story that rarely gets the attention it deserves, because the relationship between the speed of light and the equations describing electricity and magnetism is actually where the entire question began, more than a century before Einstein ever entered the picture. In the 1860s, a Scottish physicist named James Clerk Maxwell unified what had previously been treated as separate phenomena, electricity and magnetism, into a single, elegant, mathematical framework. 4 equations describing how electric and magnetic fields are generated, how they change over time, and how they interact with one another. When Maxwell worked through the consequences of his own equations, he found they predicted something remarkable: the existence of self-sustaining electromagnetic waves, oscillating electric and magnetic fields capable of propagating through empty space entirely on their own. He calculated the speed at which such waves would travel, a value derived purely from measurable electrical and magnetic properties determined in tabletop laboratory experiments involving nothing more exotic than wires and magnets, and the number that fell out of his equations was approximately 299,792,458 meters per second, a figure that matched, to within the precision of the era's instruments, the already measured speed of light itself. Maxwell recognized immediately what this meant. He hadn't assumed anything about the nature of light going in. He had started purely from the equations governing electricity and magnetism and arrived, through pure mathematics, at exactly the measured speed of light. The conclusion was unavoidable. Light itself is an electromagnetic wave, and the speed at which it travels is determined entirely by 2 fundamental physical constants: the permittivity and permeability of free space, quantities describing how readily electric and magnetic fields can form within a vacuum. Combine those two constants correctly, and the speed of light falls directly out of the mathematics, not as an arbitrary number nature happened to choose, but as an automatic, unavoidable consequence of how empty space itself responds to electric and magnetic disturbances. This is precisely what Einstein was protecting, decades later, when he built the entire structure of special relativity around the absolute constancy of light's speed. He wasn't merely protecting the speed of one particular kind of wave. He was protecting the speed of electromagnetic interaction itself, the very rate at which electric and magnetic fields are able to influence each other and propagate their changes outward through space. And once you see it this way, a much deeper question comes into focus, one that connects everything discussed tonight back to a single unified idea: why does this same number? The speed of electromagnetic waves also appear as the crucial conversion factor linking mass and energy in Einstein's most famous equation. And what does that connection reveal about what the speed of light actually is at the deepest level physics currently understands? Consider Einstein's equation relating mass and energy, the one etched onto more coffee mugs and classroom posters than perhaps any other formula in the history of science. Energy equals mass multiplied by the speed of light squared. The speed of light appears here not merely raised to some arbitrary power for convenience, but squared specifically, and the natural question, rarely asked outside a physics classroom, is why the speed of an electromagnetic wave should have anything at all to do with an equation describing the relationship between mass and energy. The answer reveals something genuinely deep about the underlying architecture of physical reality. Within the framework of special relativity, the speed of light isn't fundamentally the speed of any particular kind of wave at all. It functions instead as the conversion factor between spatial intervals and temporal intervals within the geometry of space-time itself. Space-time, remember, is a four-dimensional structure, 3 dimensions of ordinary space woven together seamlessly with 1 dimension of time. And any complete description of distance within that structure necessarily involves both spatial and temporal components together. To convert meaningfully between them, between how far apart two events are in space and how far apart they are in time, you need a conversion factor carrying units of speed. That factor is c. It represents the rate at which the universe converts spatial distance into temporal distance, or, described the other way around, the rate at which space and time interconvert within the fundamental geometric structure of the cosmos itself. Light travels at c, not because light possesses some special privileged status among all the things that exist, but because photons are massless. And massless particles are compelled, by the very geometry of space-time, to propagate at exactly the characteristic speed that geometry defines. If it were somehow possible to strip an electron of its rest mass entirely, leaving everything else about it unchanged, it too would travel at exactly c, indistinguishable in this one crucial respect from a photon. The constraint operates at the level of geometry itself, not at the level of any particular type of particle. The speed c is the geometric rate, full stop, and anything without mass simply rides along at that rate automatically, while anything carrying mass moves more slowly, paying an ever-steepening energy cost as it approaches that same rate without ever quite reaching it. Seen this way, the equation linking energy and mass says something considerably deeper than it might first appear. It says that mass and energy are fundamentally equivalent, separated from one another only by a unit conversion, and that conversion factor happens to be the same fundamental geometric constant governing the entire structure of spacetime. Rest mass, in this framework, can be understood as a kind of condensed space-time energy, and the factor of c squared is simply the exchange rate between the two, an exchange rate set not by the properties of any specific particle, but by the underlying geometry of the universe those particles happen to exist within. This framing clarifies, with unusual precision, exactly what it would actually mean to exceed the speed of light, and it's considerably stranger than simply outrunning a particular category of electromagnetic wave. It would mean moving faster than the characteristic speed of the space-time metric itself, faster than the rate at which the fundamental geometric structure of the universe is able to propagate its own changes and exert its own influence. In the discrete quantum space-time picture explored earlier, it would mean propagating correlations faster than the underlying network constituting space-time itself is capable of allowing. Not merely difficult, not even simply impossible in the sense of requiring unattainable energy, structurally undefined, in precisely the same sense that a temperature below absolute zero is undefined, not forbidden by some external decree, but genuinely meaningless as a concept, because there is nothing left within the structure of the idea to remove. There's a companion way of approaching this same deep structure, one that runs through the concept of information itself rather than through energy or geometry directly. In physics, information is never an abstract, disembodied quantity. It must always be encoded in some physical state, transmitted through some physical process, stored within some physical system, and because information is fundamentally physical in this sense, its transmission is necessarily governed by physical law. In particular, information cannot travel faster than the maximum rate at which physical influence of any kind is able to propagate, which is. Once again, see, this relationship is formalized in what physicists call causality, the principle that information flows only from cause to effect, only from past into future, and never in the reverse direction. Causality demands a well-defined ordering of events in time, and that ordering must remain consistent across every possible observer, and it can only remain consistent for every observer if the influences connecting those events never travel faster than c. The speed of light, understood this way, isn't simply the speed of one particular kind of wave that happens to be useful for illuminating rooms and transmitting radio signals. It's the maximum rate at which information can move through the universe at all. The maximum rate at which any single physical event can influence any other, the maximum rate at which the present moment is capable of shaping whatever comes after it. And the reason it holds this uniquely privileged position is that c is the characteristic speed belonging to the geometry of space-time itself, the very rate at which that geometry propagates its own changes outward. If something managed to travel faster than c, it would, in a very real sense, be acting on events before the underlying geometry connecting those events had actually finished propagating between them, exerting influence on a stage whose curtain had not yet fully risen. In a universe governed by consistent laws, by real regularities, by causes reliably connected to their effects, that simply cannot be permitted to happen. And so, across every framework physics has ever developed to examine the question, it doesn't happen. One of the more productive ways to think about the light barrier is to ask quite deliberately what the universe would actually have to look like for it not to exist at all. Suppose, purely as a thought experiment, that the speed of light were not a genuine universal limit, merely a very fast speed beyond which acceleration simply grew more difficult without ever becoming formally infinite. In such a universe, Lorentz invariance, the underlying symmetry at the heart of special relativity, would break down at sufficiently high velocities. The relativity of simultaneity would collapse, and something resembling absolute, universal time would need to be restored. Maxwell's equations, which so elegantly unified electricity, magnetism, and light into a single coherent framework, would need substantial revision. The deep, precise connection linking electromagnetism to the propagation of light would need to be severed entirely. The Higgs mechanism, which depends critically on a version of quantum field theory built on the assumption of Lorentz invariance, would need to be reconstructed from the ground up. The stability of ordinary matter itself, which relies on quantum mechanical processes that respect Lorentz symmetry at every level, would need to be re-examined from first principles. And every single prediction of the standard model of particle physics, predictions confirmed experimentally to extraordinary, almost unreasonable precision, would potentially fail. Removing the light barrier, in other words, isn't remotely comparable to relaxing an ordinary speed limit posted along a highway. It's closer to removing a load-bearing wall from the foundation of a building that has been standing, tested, and refined for well over a century. Nearly the entire structure of confirmed physics rests, in one way or another, on the constancy of C. Every component of the standard model, every prediction of quantum electrodynamics, every test general relativity has ever passed. Every measured property of every particle ever detected in any laboratory anywhere. All of it depends at some level on this single constant remaining exactly, unwaveringly constant. Removing that constancy wouldn't simply make interstellar travel more convenient. It would demolish the entire explanatory framework that currently accounts for essentially everything we've ever measured about the physical universe, and we have measured an enormous amount. Physicists have tested this constancy with a precision that borders on genuinely astonishing. The most stringent tests rely on astrophysical sources emitting extremely high-energy photons across a range of energies simultaneously. Gamma-ray bursts, among the most violent and energetic events anywhere in the observable universe, produce photons spanning a wide spectrum of energies in a single burst. If Lorentz invariance were even slightly violated, different energy photons would travel at very slightly different speeds, and over distances spanning billions of light years, even an extraordinarily tiny discrepancy would accumulate into a measurable difference in arrival time. The Fermi Gamma-Ray Space Telescope has measured exactly this, tracking the arrival times of photons across a wide range of energies from distant bursts, and the results constrain any possible violation of Lorentz invariance to less than 1 part in 10 to the 20th power. To put that number in some kind of context, the precision of our very best atomic clocks currently sits at around 1 part in 10 to the 18th power. The tests of Lorentz invariance are, remarkably, 2 full orders of magnitude more precise than our finest timekeeping instruments, and across every one of these tests, the result is the same. No violation, no hint of a crack, nothing. Similar searches using cosmic ray data, atmospheric neutrino measurements, comparisons between separated atomic clocks, and careful analysis of gravitational wave signals from merging black holes and neutron. Stars have all returned an identical verdict. Lorentz invariance holds at every single energy scale currently within reach of human instrumentation to a precision that would have seemed almost fantastical to physicists working just a few generations ago. The light barrier isn't showing the slightest sign of weakening at high energies. It isn't being subtly modified by some new undiscovered physics at any scale we've managed to probe so far. If new physics does eventually modify Lorentz invariance in some meaningful way, it must be operating at energies or scales that remain, for now, entirely beyond our experimental reach. So what would it actually take to change this picture, to genuinely open some kind of door beyond the light barrier while remaining fully consistent with everything else we already know to be true? Any viable proposal would face an extraordinarily demanding set of requirements simultaneously. It would need to preserve every confirmed prediction of the standard model of particle physics without exception. It would need to preserve every confirmed prediction of general relativity, from the bending of starlight around massive objects to the precise dynamics of binary pulsars to the detected properties of gravitational waves themselves. It would need to resolve the causality paradox embodied in the tachyonic anti-telephone, explaining convincingly how faster-than-light signaling could exist without enabling genuine logical contradictions. It would need to remain consistent with the no-communication theorem in quantum mechanics, while somehow circumventing it for some specific, carefully defined class of physical systems. And it would need to do all of this while staying safely within the experimental limits on Lorentz invariance violation, limits now measured at roughly 1 part in 10 to the 20th power. This is not, strictly speaking, an impossible list to satisfy. Physics has genuinely surprised us before, more than once, in ways nobody fully anticipated in advance. But it is an extraordinarily demanding list, and any proposal capable of satisfying every single item on it simultaneously, without quietly violating even one, would represent one of the most significant developments in the entire history of physics. This is precisely what separates serious theoretical work in this area from casual, unmoored speculation. Not that speculation itself is somehow forbidden or unwelcome within physics, but that any speculation, however imaginative, must eventually connect back to the existing, thoroughly confirmed framework in a way that preserves everything already established, while genuinely adding something new and testable to it. No proposal for faster-than-light physics has yet managed to clear that bar. Not for any shortage of brilliant people trying, but because of the sheer, formidable difficulty of the constraints involved. And once you set the raw mechanics of the problem aside for a moment, once you step back from equations and experimental bounds and consider instead what a universe genuinely governed by this kind of light barrier actually feels like from the inside, from the perspective of anyone, anywhere, looking outward at the night sky, a different and far more human dimension of this question begins to come into focus. Step back now from the equations for a moment, because the light barrier isn't only a constraint on propulsion systems and particle physics, it's the architecture of something much larger, something that shapes the entire relationship between any observer anywhere in the universe and everything that exists beyond their own immediate neighborhood. Every star visible in the night sky is a message sent from the past, and the light barrier is precisely what guarantees this will always remain true for every civilization, everywhere, without exception. Light from the moon takes roughly 1.3 seconds to reach Earth. Light from the sun takes about 8 minutes. Light from Proxima Centauri, the nearest star system beyond our own, takes just over 4 years to complete the same journey. Light from the center of our own galaxy takes roughly 26,000 years. Light from the Andromeda galaxy, the nearest large galaxy to our own, takes about 2.5 million years. When you look at Andromeda through a pair of binoculars on a clear night, the light striking your retina left that galaxy 2.5 million years ago, long before anything resembling modern humans existed anywhere on Earth. The universe you're looking at whenever you look up is never a picture of right now. It's a composite, a patchwork of countless different moments frozen at vastly different points in the past, layered together into a single sky. Some of those stars may no longer exist in the form you're seeing them. Some of those galaxies may have already merged with their neighbors in the intervening time. The present tense state of the cosmos, the universe exactly as it exists at this precise moment, remains permanently inaccessible to any observer anywhere, because light, however fast it travels, always carries only the past along with it. This has a further, stranger consequence tied directly to the ongoing expansion of the universe itself. The observable universe spans roughly 93 billion light-years across, representing the total volume from which light has had enough time to reach us since the Big Bang. But the universe itself may be far larger still, quite possibly infinite, and it continues expanding as you listen to this. The most distant regions we're currently able to observe are receding from us at speeds that already exceed the speed of light, not through any local violation of the light barrier, but because the space between us and them keeps stretching continuously everywhere at once. Light emitted from those regions today will never reach us, not eventually, not ever. Swept away by the expansion of space faster than it can make any progress toward us at all. The observable universe, already vast beyond any real intuitive grasp, represents a shrinking fraction of everything that actually exists. As time continues to pass, more and more of the universe crosses permanently beyond our cosmological horizon. Nothing about it ceases to exist when this happens. It simply becomes forever unreachable, forever unknowable, separated from us not by mere distance, but by the combined, compounding structure of a finite speed of light and an eternally expanding universe. Every galaxy beyond a certain distance will eventually cross this horizon entirely. Far enough into the future, long after the stars burning in the sky tonight have exhausted their fuel. The only galaxies still visible to any civilization that might exist to look upward will belong to their own gravitationally bound local group. Everything else, the overwhelming majority of everything that currently exists, will have receded permanently beyond reach, gone not through destruction of any kind, but through the relentless, quiet mathematics of cosmic expansion. The light barrier and the accelerating growth of space-time together draw a permanent, inescapable boundary around what any single observer anywhere in the cosmos could ever hope to know. And what lies beyond that boundary isn't merely unknown in some temporary solvable sense. It's fundamentally, permanently unknowable. Not for lack of sufficiently powerful telescopes or clever enough instruments, but because the underlying structure of the universe itself enforces this particular kind of isolation as one of its basic, non-negotiable features. This same structure carries profound implications for the search for other intelligent life, and it may quietly resolve one of the oldest open questions in all of science. In 1950, physicist Enrico Fermi, the same man who built the world's first nuclear reactor, was having a casual lunch with colleagues when the conversation turned to recent newspaper coverage of reported unidentified flying objects. After a bit of rough calculation, Fermi posed a deceptively simple question that has echoed through physics and astronomy ever since. If the universe is as old and as large as it appears to be, and if intelligent civilizations are reasonably common within it, then where is everyone? Why the silence? Countless answers have been proposed over the decades since. Perhaps genuinely intelligent life is far rarer than we tend to assume. Perhaps civilizations reliably destroy themselves before ever becoming capable of interstellar travel. Perhaps they're already here in some form, and we simply lack the tools or the awareness to recognize the signals. But one possibility fits with unusual precision alongside everything we've explored tonight. Perhaps interstellar travel really is simply too difficult, not merely for humanity at our current level of technological development, but for any civilization, at any level of development, anywhere in the universe, forever. A civilization 1,000,000 years more advanced than our own still lives inside the same universe we do, still bound by the exact same equations, still facing the exact same light barrier. The energy required to accelerate any spacecraft carrying living beings up to a meaningful fraction of light speed, to sustain that acceleration across the years such a journey would require, and then to decelerate safely again at the far end, remains staggeringly large under any reasonable estimate imaginable. Even a civilization that somehow solved the energy problem entirely would still face the time problem waiting patiently behind it. The Milky Way alone contains somewhere between 100 billion and 400 billion stars, meaningfully exploring even a small fraction of them. Even travelling at velocities extraordinarily close to the speed of light would require spans of time comparable to the age of the universe itself. The distances involved aren't simply large in the ordinary sense of that word. They exist in an entirely different category from anything human civilization has ever had to reckon with, and the light barrier ensures, as far as current physics can tell, that they will remain in that category permanently unless one of the geometric loopholes explored tonight somehow proves to be both real and genuinely accessible after all. Which may be exactly why physicists keep returning to this question, decade after decade, not out of naive optimism, but out of an honest, disciplined desire to know, with real precision, whether this universe permits any civilization to ever truly leave home. There's one more consequence worth sitting with before we bring tonight's exploration to a close, because it reframes everything that's come before it into something quieter, something closer to a genuine philosophical fact about the shape of existence itself. If faster than light travel is genuinely, permanently impossible, and if intelligent civilizations exist scattered across interstellar distances, then every one of them, ourselves included, sits enclosed within what might reasonably be called a light cone prison. Not a prison in any sense involving suffering or confinement in the ordinary meaning of that word, but a prison in the precise, topological sense used by physicists, a region of space-time from which only certain events can ever be reached, and beyond which nothing at all is accessible, regardless of how much time or effort or ingenuity is applied to the problem. The future light cone belonging to any observer represents the complete set of space-time events that could, in principle, ever be reached from their current location while travelling at or below the speed of light. Everything inside that cone remains reachable, at least in principle. Everything outside it is not, and never will be. As time passes, this cone does expand outward, continuously, moment by moment, the boundary of what's theoretically reachable growing steadily larger, but it expands at exactly the speed of light, no faster, while the universe itself continues expanding around it, and the net result of these two competing processes is genuinely strange. Some regions of space that remain within reach today, that a signal or a sufficiently ambitious spacecraft could theoretically still reach if launched immediately, will, over the coming billions of years, be swept permanently beyond that light cone by the relentless expansion of space-time itself. They will become forever unreachable, not because of anything any civilization did or failed to do, not through any failure of ambition or technology, but simply because the universe expanded them beyond reach while everyone capable of reaching them was still alive and watching. This means the light cone prison has walls that are quietly closing in, not from every direction at once, but specifically from the outside, as the accelerating expansion of the universe steadily shrinks the total volume of space that will ever be permanently accessible to any given observer, no matter where in the cosmos that observer happens to be located. It's one of the stranger, more genuinely humbling consequences of living inside an accelerating, expanding universe governed by a hard light barrier. Every civilization that has ever existed or ever will exist is embedded within its own slowly shrinking sphere of cosmic accessibility, and there is, as far as physics currently understands it, absolutely nothing to be done about it. It is simply woven into the basic nature of the universe every one of us happens to have been born into. And yet, despite everything explored tonight, despite every obstacle, every closed loophole, every theorem constraining the possibilities down to something vanishingly narrow, the research continues seriously, rigorously, without any sign of slowing down. The people working on warp drive geometries today aren't dreamers detached from reality. They're credentialed physicists publishing in peer-reviewed journals, building carefully on each other's work in the same methodical way physics has always advanced. The subliminal warp bubble, requiring only ordinary matter rather than anything exotic, is being actively developed as a genuinely achievable long-term goal, one that could eventually transform travel across the solar system and to nearby stars from a matter of millennia into a matter of years. The energy condition theorems are being carefully re-examined for hidden assumptions that might not survive contact with a completed theory of quantum gravity. The quantum energy inequalities are being refined and tightened further. Experiments testing Lorentz invariants continue pushing toward ever higher energies and tighter precision, not because physicists expect a violation to appear, but because the history of physics has taught them, repeatedly and unmistakably, that the universe still has room to surprise us in ways nobody has yet anticipated. Quantum mechanics wasn't predicted in advance from within classical physics. It was forced into existence by experimental results classical physics simply couldn't explain, no matter how hard anyone tried to make it fit. General relativity wasn't predicted from within Newtonian gravity either. It was forced into existence by a genuine conceptual inconsistency between Newtonian gravity and special relativity, and then confirmed decisively through careful observation. The history of physics, examined honestly, is a history of the universe repeatedly turning out to be stranger than anyone expected, not typically in ways that break causality or overturn the light barrier outright, but in ways that reveal entirely new layers of structure nobody previously suspected were there at all. Whether the universe still has surprises of that magnitude waiting near the light barrier, surprises that don't violate causality, but that reveal something we simply haven't found yet, remains genuinely, honestly unknown. Physics doesn't know the answer, and its willingness to say so plainly, without pretending otherwise, remains one of the most trustworthy things about it. What lies beyond the speed of light, then, isn't a single sentence, and it never really was. It's a carefully built structure of reasoning layered from 5 independent directions, each one arriving, through entirely different mathematics, at essentially the same conclusion. Nothing with mass can reach the speed of light through any conventional means, confirmed beyond any reasonable doubt. Faster than light particles remain, at best, an elegant mathematical possibility with no experimental support after more than 50 years of dedicated searching, and the word once used to describe them now does far more useful work describing instability itself, the very instability responsible for mass existing in the universe at all. Causality forbids faster than light communication categorically, confirmed across quantum mechanics, quantum field theory, and general relativity independently. The geometric loopholes offered by wormholes and warp drives are real in the mathematics, but sealed by exotic matter requirements, navigational lockouts, radiation hazards, and rigorous topological theorems that leave almost no room to maneuver. And at the deepest level physics can currently reach, the light barrier may not be a limit imposed on space-time from outside at all, but a fundamental property of space-time's own underlying structure, as intrinsic to it as the speed of sound is to the material it travels through. What remains underneath all of it is a universe built on genuine consistency, where cause reliably precedes effect, where distant civilizations are separated not through hostility but through geometry, and where every point of light in the night sky is quietly, faithfully telling you about a moment that has already passed. The barrier isn't cruelty, it's structure. It's the reason the universe holds together at all, the reason physics works the same way everywhere, for everyone, without exception. And standing at the edge of what's currently known, asking honestly what waits beyond it, and accepting that the answer may be permanently out of reach, is not a failure of curiosity. It's the most honest thing science can offer. If tonight's journey into the edge of physics kept you company, take a moment to like this video or subscribe. It helps this channel keep bringing these long, quiet explorations to more curious minds like yours, and it costs you nothing but a second. Somewhere out there, starlight is still arriving that left its source before you were born, carrying nothing but the past, and asking nothing of you but that you look up. Good night.